Okie doke. Yesterday we talked about measures of what? Central tendency around the mean, median, mode. That's good to a point. But what if you had two data sets that had the same mean or the same median? How can you tell which one's more accurate? Now we're looking at standard of variance, because what we're looking for is what this does is, let's say we had two data sets that both had the same average, and they had some other ones, other data points. So, but the average was the same. Let's say it both equaled 50. A perfect example of this would be paint. If you go to the store, like Home Depot or Lowe's, and you buy paint for your house, they'll always say lasts an average of 20 years or 25 years. What does that mean? If the advertisement says it lasts an average of 25 years, what does that mean? Because what does average mean? So if it's at an average of 25 years, let's say 25 instead of these. What that means is you can have data that goes less than 25 and then greater than 25. It's just, if the average is 25 years, that means you take all the samples they did and divide by how many you have, and that tells you the average. So that means every gallon of paint you're going to buy lasts 25 years? No, you could be unlucky and you're out in 3 to 5 years. Was that? How do they test it? They take hundreds and hundreds and hundreds of samples, paint like a 1-by-1 sheet of wood, and put it out in the sun. And they wait to see how long it takes before it starts. That's the old days. Now they have pressure and they can speed up time. In other words, they go through all the elements of rain, cold, hot, all those other things. Because in cold, the wood constricts. In heat, the wood extracts. So that loosens the bonds of the paint. So that they go see and they start recording, when do these things start failing? And they always, almost all across the board, have 20, 25 years of life expectancy. But again, that's not what you're guaranteed. You're guaranteed that if you buy 100 gallons of paint, that 25 of those will last you 25 years. Some of them less, some of them more. So how do we determine which brand of paint we decide to choose? That's what we look at, measures of variation. In measures of variation, we look at how far on the average do the data sets vary to both sides. What does variation mean? Changes from the norm. That's a variation. So the larger the variation, the worse the paint. The larger the variation, the less accurate the measures of central tendency. More so than anything is the mean. Does the mode have anything to do with it, with quality of paint? No. How about the actual median? If we look at the length of time before it starts peeling, yeah, then the median could be qualified. The mean, same thing there, is you take all the data set and find the average of it. So the mean and the median become in question. So we're going to get 3 numbers today. We're going to get the range, the variance, and deviation. So what do you think the range is? How do you think you calculate the range? Very good. So how do we calculate the range? Subtract what from what? Ah, backwards. Yes. The range is the largest value minus the smallest value of your data set. Or we look at the maximum minus the minimum. Now, is the range resistant? Why not? And how do outliers relate to range? Well, these would be the outliers. The outliers are the points that are outside of everybody else. So these would be your outliers. So if you have an outlier that's really far off everybody else, that would be either your minimum or your max or both. So it's not resistant. And the range doesn't take in consideration any of the other points in between those. Does not take into account any of the other data values. Here's our first example. So again, the range is simply a number that tells us how far from the lowest to the highest. Again, how can we relate this back to the paint? Well, if our averages are 25 and the range of sample A is 60 and the range of sample B is 35, what does that tell you about the 2 samples? Okay, they both have an average of 25 years. Sample A has a range of 60. Sample B has a range of 35. Does that help you make your decision which paint is better? It should. Because if the range is 60, that means I could either get the lowest end or the highest end, which is 60 years span. That doesn't help me much. But if it's 35 years, that means the paint is more the crappy paint and the good paint are closer together. So the smaller the range, the more condensed your data. So that's your first measures of variation. The wider the range, the more dispersed the data. So here's our first example. Find me the range of this data. Yeah, so the range is the max minus the min. So what's the highest one? That's the max. And lowest? So that's your first thing. You have to find the highest and lowest. 55.6, 14.1. So it's 41.5. Last time we used the same data points, we found the average. What was the average last time? Yeah, 30.7475. So what does that tell you? If the average is 30.74 and the range is 41.45 or 41.5, what does that tell you? What it should give us a picture like this. So between our highest and lowest points, this is the min, this is the max, this is 14.1, 55.6. The average comes in about at 30.74. That's not pretty good. It's actually terrible because you're looking at about 16 this way, 16 that way. 16, 20. So that's a pretty bad spread. I mean, their cellular system isn't too reliable. So what we have to then, since the range doesn't help us much, we have to look at now how this data is dispersed throughout the mean, from the mean. That we look at the standard deviation. The symbol we use for standard deviation is the small letter S. As you can guess, the deviation is how far the data values deviate from the mean. And we have two formulas that we'll be dealing with here. One of them is is Essence is like a shortcut. The other one is the standard one we always use. So here's the first one. And I'll walk you through with how we derived this, what it really means, where it came from. First off, let's find, what does X represent? The data values. What does X bar represent? The mean of the data. What does N represent? Very good. Remember, the standard deviation, the deviation means what? How far something goes away from the mean. So let's look at the first part. How we got that formula. First, we have our data set. So it's just a bunch of numbers, just a bunch of data set. Then we find the mean of that data set. So let's say it's the middle number. It's towards center. What we're looking for here is we're looking how far the data deviates or moves away from the mean. Determine how far each data point is from the mean. How do you find how far the data point is from the mean? What do you use to calculate that? The same way we found the range. We have this point. How do we know how far these two numbers are? Yeah, so let me put some values here. Let's say we had 2, 5, 5, 6, 7, 8, 8, 9, 5, 8, 9. So we have our data set. What's our average there? So get your calculator out, add them up. What's that? 2, 4, 6, 8, 10, 12. Okay, so let's look where I'll use this then. My data is 2, 5, 6, 7, 8, 9. The frequency of those are 1, 3, 2, 1, 3, 9. Let's see how far these are from the average. And the average, how do we find that? If we add up all of our X's, what does that give us? Nothing really. If we add up all of our frequencies, what does that give us? Well, that's 1. Oh, it's 2. I mean. So we get 3, 6, 9, 12. So the summation of all your frequencies is your N. It tells you how many pieces of data you have. So how do we find the average now with this type of data set? We first, whenever we have frequencies, we have to take our value times our frequency. So 2 times 1 is 2. 5 times 3 is 15. 6 times 2 is 12. 7 times 1, 8 times 3, and 9 times 2. So now we add up all of our X times F's, and that gives us what? So that's 30. What is it? 78. So that allows us to find our average. Our average is the summation of all our XFs over all of our frequencies, which is summation of XF over N, which is 78 divided by 12, which is 6.5. That's our average. So far, so good. So we know this is our average. Let's look at now, how far are our numbers away from our average? How do we do that? X minus X bar. So how far is 2 minus 6.5 is what? Try again. What is that? Negative 4.5, yes. 5 minus 6.5. Five minus 6.5. Without a calculator. Negative 1.5. Very good. 6 minus 6.5. Very good. Negative 0.5. 7 minus 6.5. 8 minus 6.5. And 9 minus 1.5. 9 minus 6.5. Okay. If we added all these up, what will we get? Well, clearly, these two would cancel. These two would cancel. Actually, ideally, if we did this each one separately, all the ones to the left would cancel with all the ones to the right. Let's look at. I'll show you what I mean. So we have 2, 5, 5, 5, 6, 6, 7, 8, 8, 8, 9, 9. Okay, so here's all our individual data sets. If we did this, there's 6.5. We took each one of these minus 6.5. So this would be negative 4.5, negative 1.5, negative 1.5, negative 1.5, negative 0.5, negative 0.5, 0.5, 1.5, 1.5, 1.5, 2.5, 2.5, right? Now, these are each of our individual data points. This is how far away I am from mean. So these two cancel. These two cancel. We have another 1.5 and a negative 1.5. They cancel. So we have negative 4.5 minus 4.5 is negative 5. 2.5, 2.5 is 5. So it becomes 0. Ideally, that's how you test to see if it's a true average. If it's a true average, it means every number that's smaller than it equals every number that's bigger than it. That's what you're looking for. That doesn't help us much, does it? Why not? What ruined it for us there? It took away all the data. So if we got rid of, the only thing mathematically we can get rid of is these negatives cancel the positives. We're looking for the distance between our points, aren't we? Yeah, so what we're looking for is, in reality, we can never have a negative distance. Distance is an absolute value. In other words, if you live in Grand Prairie, Dallas, or Fort Worth, they're a positive distance away. So what we have to do is we have to get rid of the negatives. How do we get rid of the negatives? If you square a number, what happens to it? It always turns positive. So let's look at this one. Let's do all these separately first. So negative 4.5 squared. Your use calculator. (20.25). Negative 1.5 squared. So that's 2.25 again. That one's 2.25 again. Negative 0.5 is 0.25. 0.25, 2.25. So these are the positives, 2.25, 2.25, 2.25, 2.5 squared. Well, you have the numbers. You have the calculator, don't you? Square them. You don't have to. You don't have to, because it's always gonna be positive. No. What are you squaring? 4.5 times 4.5.
Oh, okay.
Just do that if you don't have a square button. Okay, what happens if we add up all these? These are all our distances from the mean. So add them all up. 1, 2, 3. This is 1. So all these equal 27. That equals 1. So that equals 3. 1 was 13. Equals 43. Let's see what you got, same thing. No, hold it. This is 17. 47. 6, 10, 12, 14. 6, 6 is 12, 13, 14, 17. Yeah, so it's 17. So it's 47. So what's our average distance? We know we have 47. So 47 divided by 12 equals what? Three point something. That's pretty large. Why is that pretty large? Because if our average was 6.5 and if we added all these, we got 3.91. There's something not right here. So what is the difference here? What's the problem? When we got rid of the negatives, we made the numbers artificially large. So how do we shrink something that we square rooted? That we squared. What's the opposite of squared? If we square root the numbers, what does that do? Well, if we square root 20.25, what do we get? We should get 4.5. If we square root 2.25, we should get 1.5. Except we got rid of the negatives. So you see, mathematically, we looked for the distance. Anything to the left of the mean is going to be negative. Anything to the right of the mean is going to be positive. So we squared them to get rid of the negatives, and we square root them to get rid of that square, because we're back down to the normal sizes now. So what our formula tells us to do now is we have to go through each of our data set and square them. So this becomes 20.25. This one becomes 2.25. This one becomes 0.25, 0.25, 2.25, and 6.25. We squared all the numbers. We got rid of the negatives. And if we add up all those, we get 31.50. So go ahead and verify me, make sure I'm correct. So if you add up all these, you should get 31.5. There's not much work to do here. Just copy the numbers, type them down in your calculator, hit plus, hit plus, hit plus, hit enter. I mean, if you're having trouble with that, then that's another issue we have to have. You left off some numbers. All right. So now we can find the average of this. Here is the issue. Because we're trying to approximate our population, we take this number, we just have this number here, which is the summation of all of our X minus X bars squared. Now we divide by N minus 1. One way you look at this is to get rid of our outliers. Or we're trying to approximate the population. So remove any inappropriate numbers there. So again, we had 12 numbers. Now we divide by 11. So we have 31.50 divided by 11 equals 2 point something. 96, 86. We're getting closer, but that's still pretty large. How do we get back down to regular numbers? How do you get rid of the square? Square root it. So now what we do is to find what's called the standard deviation, we square root our formula. So we square root this number. So the square root of 2.86 is what? This tells us how far on the average our numbers are away from the mean. On the average. Again. So let's look at the formula we have here. This is mechanically how we do it. We find our numbers, subtract it from the mean, and then square them, and then square root them. So the formula we're looking at here is this. You have to build it. You have your data set. You have to find the mean, subtract them, square them, divide it by n minus 1, and then square root it. That's to find the standard deviation. Now, the shortcut method. This is formula 2. The standard deviation becomes n times the summation of x squared minus the summation of x squared divided by n times n minus 1. Why is this the shortcut method? You don't have to find the mean. It takes it already into consideration. So the properties of the standard deviation measures how far from the mean each value lies. S is that. Okay, here's a thing you have to be careful about. If you used Excel or a calculator or your cell phone, they can give you different answers for the standard deviation. You enter all the data points, hit standard deviation, it could give you a different answer. Why? Because most calculators use the second formula to calculate the standard deviation. Why? Because you don't have to find the mean. All you do, you have your data points, you add them up, you have n, that's all it takes. There's no other calculations you have to do. So if your numbers come out to be different from method 1 and method 2, method 1 is the recommended one we use mostly in mathematics. So take it with a grain of salt, but if you're calculating it, calculate it the first way because it's more accurate. Let's look at example 2 here. Use formula 1 here. Actually, we just did that actually, didn't we? No. No, was that? The formula 1 is the one the first one we did. The summation of x minus x bar squared over n minus 1. That's method 1. So go ahead and look at those and do those. Because then we're going to do the same thing with the second method. So for our formula, what's the first thing you have to find? Yeah, we have the x's, we don't have the mean. So we have to find the mean first. You find the mean by add up all your x's and divide by how many you have. So the average is 153.7 divided by 5, which makes it 30.74. So that's our average. What do we do with the average? Yeah, look at the formula. Whenever you try to create these charts given a formula, work inside out. So we have x and we have x bar. So now we have to do x minus x bar, which is 30 minus 74. Okay, so we have the x minus x bar. Now what do you do with it? Nope. We just built the x minus x bar. We have to square each of those. We have to square each of those. X minus x bar squared. We have to build up this equation. So what values did you get? The first one, 276.88. Next one. Next one. Next one. And last one.
618.1.
Thank you. So we have all of those. We have the x minus x bar squared. Now what do we do with them? Nope, we have to add them up. So now this gives us our summation. If we add up all those, what do we get? Point oh one. So we found the mean first, x minus x bar. Then we squared those. Now we added all those up. Now we have to divide by n minus one, which is 1083.01 divided by n minus one. What is n? So this is 5 minus 1.
$207.
270. And then we do what with it? Now we square root it. Equals what?
Uh, 16.35.
So that is our standard deviation for our data set. What you have to do is you have to look at the formula and build it from the inside out. Okay, now let's look at the example for using the second formula. The same data set, but this time we're going to use this one. So we have the same data set. 14.1, 22.4, 23.1, 38.5, 55.6. N equals 5. Now, building our formula, what do we need? We have N. So let's look at the first one. Well, let's look at this one here, actually. What does this one tell us to do? Yeah, add up all your X's and then square it. So our first thing we have to do is find summation of X. You're adding all the X's. And 17. 153. So our summation of X is equal to 153.7. Put everything back here. So this is N summation of X squared. All right. So while we start building this thing out, we know we have N. We have the bottom already done. So summation of X is 153.7, and we have to square that one. What are we missing? What's our first one missing? What does this tell us to do? We have to add up all our squares. So we have to square all the X's first. So we have to square all of our X's and then add them up. So that's 198.181. $22.4. 22.4 squared. 501.76. 23.1 squared. 533.61. 38.5 squared. 1,482.25. 55.6 squared. 3,091.36. 3091.6 plus 1482.25 plus 533.61 501.76 plus 198.81 equals 5,808.03. Once I put them in the formula, now I'll just do it mathematically. So 5 times 5,808.03 $29,040.15 $153.7 $23,623.69 5 times 4 is 20. $29,040.15 equals 16.45. Which is what other one was.
Do we consider rounding Taylor?
You're supposed to, but no, give or take a few points, it's gonna be close enough. You're right, because our answers, remember, our answers are supposed to be one decimal place more than our data set. But yeah, there will be rounding off errors because as you square these numbers and square root them, and yes, there will be rounding off errors. Yeah, I should have gotten 46 because it was mine was 456. So I should have 46 right here. But yeah, you'll have rounding off errors that way. But that's the way we do it. Now, what are all these things used for? The range rule of thumb for standard deviations. The rule of thumb is this. And we're going to look at the chart of this in a little bit before we leave today. It says that 95% of our data will fall within 2 standard deviations from the mean. So it says 95% of our data will fall within 2 standard deviations of our mean. So if here is our mean, we have 1 standard deviation, 2 standard deviations, minus 1 standard deviation, minus 2 standard deviations. So what does that mean? What does that tell us? Example. If the mean was 50 and the standard deviation was 10, so if this was 50, a standard deviation is 10, which means from 50, if we add 10, we get 60. If we add 10 more, we get 70. Go the other way. If we had 50 and we take away 10, we have 40, we have 30. So it says that between 30 and 70, the values 30 and 70, 99.5%, or not 95% of our data will fall within this range. That's what it's telling us. Within 2 standard deviations. Which means what? Which means significantly, most of our data is within 2 plus or minus 2 standard deviations, 2S. Anything over here is called significantly high. Anything below here is called significantly low. Those are the ones we're looking for. Anything here is really not that significant. Since a lot of the data happens there, it's not significant. You don't really stand out of the crowd if you sit in that range. But if you're significantly high, significantly low, outside the 2 standard deviations, that's what we're interested in. So let's look at our last example. Our standard deviation was 16.45. Our mean of the data was 30.74. What are 2 standard deviations of that data set? No. So if the mean was 30.74, then 1 standard deviation would be 47.16. That's 1 standard deviation. 2 standard deviations, so add 16.45 to that. That's 2 standard deviations. So minus 1 standard deviation would give us 30 minus 16 is 14. .14. Or something about that. So, and if we take away 2 standard deviations, it would be 0.25, something like that. So are these numbers correct? I didn't think it was. So the average is 30.74 minus our standard deviation was 16.45. So it's 14.29. And then 14.29 minus our standard deviation, which is 16.45, gives us negative 2.16. Which tells us that within 2 standard deviations, we have 95% of our data in there. It just so happens that's 100% of our data in there. So anything outside the 2 standard deviations is either significantly high or significantly low. Anything in the middle is really not significant for us because it's the majority of our data. Rule of thumb for estimating a value of the standard deviation. S. This is an approximation. This is very rough. To find the standard deviation, take the range divided by 4.
Divide by 4.
Divide by 4.
For us, it would have been 10.2.
Yeah, so 10, 16. Again, it's a rough, very rough approximation. It's not accurate, but it's a rule of thumb. Remember, you're estimating the standard deviation. So take the range divided by 4, and it'll tell you if how your number should look. All right, here's for this example. Using the data from the book, the mean is 17.6. The standard deviation is 16.02. Use the range rule to find the limit separating the values that are significantly low or significantly high. So is 77.8 significantly high or is it insignificant? How do we figure this out? Figure out if it's high or low. Take the mean, add 2 standard deviations. Find if it's low, take the mean and subtract 2 standard deviations. So we have 17.6 plus 2 times 16.02. Which makes it 49.64, right? So is this number higher than 49.64? 77.8. So since 77.8 since 77.8 is larger than that, then it's significantly high. It's larger than 2 standard deviations away from the mean. If it's low, we just subtract standard deviation to see if that works. Yes, that's looking for. All right, let's look at this next example. Sample of 50 data sets. Those 50 values have a minimum of 0.8 and a maximum of 77.8, and there are 50 of them. So how do we find it using the second formula, the shortcut? So it's the max minus the min divided by 4. 77.8 minus 0.8 over 4, which is equal to 77 divided by 4. But what?
25.
25, yeah. So it's telling us the standard deviation is approximately 19.25. Again, what was the real standard deviation? We had was 16 point something, right? So that's still pretty close. 16.45. Again, it's a rough estimate. Sample versus population. Standard deviation. Basically, if you have our alphabetic letters, it's the sample. If you have Greek letters, it's the population. So for the, what does S stand for? Standard deviation. In the population, if you see it, it's the row symbol. In sample, we use the little n. In populations, we use the capital N. So that's other than that, everything else is the same. In other words, in our standard deviation formula, that's the difference. Oh, I forgot nothing. Since we're dealing with the Greek letters. The mean is the mu. MU. Again, if you have Greek letters, it's population, and you have to use always the Greek letters in there, whatever you can, or the capital letters. If it's our alphabetic letters, then we'll just leave it alone, the small ones. One more thing. The standard variation. Dispersion or spread of the data. Besides variance, and we use variance, or dispersion or spread. You'll use any of those words. They mean the same thing. This is probably one of the easiest formulas you'll ever learn. There. That's it. That's the variance. Just square your standard deviation. Or if you have population, it's just squared. It is the square of the deviation. Yeah, here's some properties for it. Because it's squared, it's never negative. It can be equal to 0. But it can never be negative. Outliers affect the value dramatically. I mean, it changes it pretty big because we square it. It's always positive. Outliers affect the value. And that's it. Those are the big ones. We talk about the bell curve. You hear the bell curve a lot. What does it mean? We talked about the shape of it earlier. So the bell curve is a distribution where 68% of all the data fall within one standard deviation of the mean. Two, 90%, 95% of all data fall within two standard deviations of the mean. And lastly, 99.7% of all data fall within three standard deviations. Yeah. So we say is that I'll show you a better picture than this. So here's our mean. So within one standard deviation, we have 68% of our data. Within two standard deviations, we have 95% of our data. And within three standard deviations, we have 99.7% of our data. So here's a quick question for you. How much are in both of these end? So what percent of our data is greater than three standard deviations? No, that's two standard deviations. Close though, good try. Let's look at this. We know that around about the mean, one standard deviation is 68%, right? So that means 34% is here, 34% is here. Now, in two standard deviations, we have 95% from here to here. But we have 68 taken care of already. So 95 minus 68 is 27 that's left. What's half 27? 13.5. So between the second standard deviations, that's 99.5%. How much is in this last area, the third standard deviation? Well, 99.7 minus 95 is 4.7. Yeah, half of that is 2.35. Well, we know that the last part, since that's 99.7%, is 0.03 for both of those. Total of both of these is 0.03. So half of 0.03, 0.015, or 1.5%. This is a rough approximation, of course. So you see why I told you earlier in law school, they have bell curves. 1.5% of the people make A's, 2.5 make B's, C's, and D's, and everybody else fails. I'm gonna show you the picture of the actual, what, remember, this is using the rough numbers. Here it is in actuality. So within, it's approximately 68%, West standard deviations, 34.13, 34.3. This is more mathematically accurate. Then it's 13.59, 2.14, 2.14, 0.13. And we'll pick up from here next time, because class is over. I know we had a late start because of that the lockdown drill. Okie doke. We'll finish up the chapter tomorrow as well.